Hi guys, today we're going to be doing further mathematics, the probability and statistics variant, paper 4.2 of the October-November series of 2021. So let's get started. Right, so for the first question it involves for confidence interval. So let's solve for this. A 95% confidence interval for the difference between, okay, so let's go over here, here. This is what we would need. Okay, this time it's a large sample, fine. So let's find the 95% confidence interval for this. So to do this, firstly you need to find the S2 of x and S2 of y. So let's solve for both. S2 of x equals to the sum of x, no wait, it's going to be the 1 divided by the number of terms of x minus 1, so 1 by 39, and then bracket it. And then we're going to put sum x squared, which is 14320. We subtract that with 752 whole squared, whole divided with number of terms of x, which is 40. So this is our s2 of x value, and let's plug this into the calculator to get the exact value. So right, so the value we get is 304 over 65, or 4.67, so on. So we have here 304 over 65, which is the same as 4.67. Let's keep it a 4 significant figures, 7. Now let's find S2 of y. So I'm going to take this in different ink and solve for S2y. S2y equals to 1 divided by number of terms of y. Number of terms of y is 60, so it's going to be 1 by 59. Okay, and then we multiply that with sum y squared, which is just 40,200. So 40200 minus that with 1548 whole squared divided with number of terms of y, 60. And this should be our S2 of y. So let's put that also in the calculator, just to note our fraction value here. So 1 by 59, then we have 40200 minus 1548 squared over 60, which is 1308 over 295. Over 295, which is equal to 4.434. Okay, yeah, now that we've done that, one thing I forgot to calculate some values here that we need to calculate earlier on. So let's get the sample mean of x and y. Okay, so what this denotes is sample mean, and that is the total number of samples divided by number of samples. So total sum of samples divided by number of samples. So 752 over 40 would give us our first sample mean, which is 18.8. Okay, next I'll have sample mean y, and this is equal to 1548 divide that with number of terms of y, which is 60, is equal to 25.8. Okay, so these are values that we have here. Next we need to do is calculate S2 or S2 of P. Now we calculate the pooled estimate, which is S2P, when it's stated that both population variances are equal. Nowhere does it specify any such thing, so we're going to calculate S2. Now to calculate S2 we have to do, let's take this in a different one. Take S2. So S2 is equal to S2 of X divided with number of terms of X, which is just nx, plus S2 of Y all divided by number of terms of Y. So if you just repeat this, you can get with the values you can get S2. So over here we have, okay, I'm gonna put in the decimal values over here so that I don't need to overlap. So 4.677, all divide this with number of terms of X, which is going to be 40. We add this on with total number of terms in Y is 60, and this is 4.434. Right, so when we add this we get our value. So what I'm going to do here is going to do 304 by 65. That is our value, right? Yeah, okay. So 304 over 65 divided by 40 plus 4.434, I'm going to take it as 1308 all divided by 295, and we just time multiplying it with the denominator, in this case 60. So our S2 value becomes 0.1908. So but remember, our fractional value is going to be stored here. This is what we need, by the way. Okay, now finally, for finding the confidence interval, the very crucial part, so CI is equal to, so since we have a large sample, we are not going to be using any values from the t-distribution because it doesn't correspond to any of these. So we're going to be using a rather smaller sample size. So we just have this right here. Okay, and we just need the p-value for this. To find the p-value, we just look at the middle section of it. Okay, but before we go for that, let me just label this. So it's 0.95. Remember, 0.95 as a 95% till 1. Okay, let's just say this is a distribution graph. We're looking at a confidence interval from this to this. So that means our p-value becomes right in between this, which is 0.975. Right, so that means that our p-value is going to be 1.96 because it corresponds with 0.975. But we should know that our z value is 1.96. Okay, since we are referring to our z values, I will put after this plus or minus. Yeah, so let's refer to our z value and then whole root that with S2. Okay, so we have here, let's root our S2 value and times it with our Z 1.96. Okay, so mean X minus mean Y, that is going to be 18.8 minus 25.8. So you can do this mentally and you get negative 7.0 plus or minus, and when we did this calculation right here we got 0.856. Okay, so let's do negative 7 minus this answer. So when we have a plus or minus operator, which one do we do first? To calculate the first value of a confidence interval, we do the negative operation first, and we get negative 7.86. So have here negative 7.86. Okay, and on the other side, which is going to be a positive operation, I am going to retrieve our value by doing negative 7 minus this. Okay, yeah, now we're going to add that with negative 7. We get negative 6.14. Okay, and that sums up everything that we need to do for the first question of confidence intervals. Yeah, that's pretty much it. Okay, moving on. Show how the expected frequency for this and this is obtained. So firstly, we need to know that the mean is 125, standard deviation is 12. Not very useful for this, but fine, sure. Sample size is 60, and yeah, okay, everything's to 2 decimal places. Show how the expected frequency is obtained. Okay, so we're trying to find for this column right here, how is it going to be 13.97? Okay, so for this is once again maybe a little bit difficult for a few, but it's not really that hard. So what we're going to do is we're going to subtract the mean and divide it with our standard deviation. What I mean is that 130 right here minus that with our mean, which is 125. I whole divide that with our standard deviation. Okay, so this is one general thing that we need to know. And then this will be in between. Instead of x, we do z. Okay, so z. And the reason for this is because in our earlier statistics based question, we have here test statistic minus mean whole divided by standard deviation or sigma. It's similar to that, except that our test statistic and we have the correction here. This is not too important, but the test statistic w is just replaced with x, and so you get your z value. Okay, so that's how we derive our z value there. Yeah, so z, wait, it's going to be greater than equal to z and lesser than, so when you do 140 we get this. Okay, so when we do this we get 5/12. So that means that it's going to be p over of p of 0.4167 67. Okay, and this is going to be in between z, and it's going to be lesser than 15/12, which is 1.25. Right, okay, now that we have this state right here, this is where we use our distribution graphs, the normal distribution. So over here, right there. Yeah, so we have here the first let's take as this. So there's a general formula that we know in CRV, where if you want to find the probability of x lying between a and b, we get f of b minus f of a. Right, that's the general formula for CRV. But now if you want to find for the normal distribution kind of thing, it's simply going to be using the same analogy. Phi of, wait, no, that's not phi. Yeah, it's going to be, does phi look like, yeah, so it's going to be this. It's going to be the phi of b minus phi of a. Okay, so that means phi of 1.25 minus phi of 0.467. Okay, so moving on, let's do phi of 1.25. So we can go here 1.2, and our third decimal place, I mean second decimal place is here. Right, so we have 0.8944. right? And we subtracted that with the 5 of this. So how do we calculate this? It's going to be, okay, first decimal place is 0.4, second one is 1, so it's corresponding to this. Third one, it is 6, 7. So we take this as an entire 7 value here, and so we add that 25 to this. What they mean 25 means you add that to the last two digits, so 0.6591 plus 0.0025, which is equal to 0.6616. So that's our value right there. Okay, and let's perform the subtraction right here. 944 minus our answer, which is equal to 0.2328. So this is our expected frequency when our sample size is 1. However, when we have it to 60, then we have for our sample size is 60, so we multiply that with 60, so 0.2328 times 60, and if I'm not wrong, this should be 13.97, yeah. So it is going to be 13.97, and that's it. Yeah, okay. Now moving on, carry out a goodness of fit test at 5% significance level to test whether the claim is supported by the data. Okay, so to calculate the test statistic, first we need to validate each expected frequency. To do that, we need to ensure that each expected frequency is above 5, and as you can see, the first one isn't. So what we have to do is just combine it with this one. Okay, so we're gonna have here, let's see, so 1.12 plus 5.22, this should be 6.34. Since this is test statistics based, I'm gonna just check it out just in case. Yeah, 6.34. Okay, and we're gonna have here 13.97, 19.38, 13.97. Oh, it's a repeat of 13.97 apparently. Okay, and 6.34. Fine. So this is basically our test statistic that we need to have. Okay, this is what we're going to use. This is the basis of our calculations. So now that we've combined it, we get 6.34, and the general formula for this is going to be sum of the observed value minus the expected value, and we whole square the difference between the observed and expected, and we divide that with the expected value itself. So based on that, we gotta do for everything, and we have to ensure that each e value is greater than 5. So now that we've done that, we can proceed with this calculation here. So we're gonna get, okay, so our observed value for the first one, we're gonna combine these two rows, we're gonna combine these two columns, so that means we combine the two observed frequencies as well. So it's gonna be 3 minus this expected value. Fine, so let's just see, 3 minus 6.34 whole square divided by 6.34. It's going to be 1.7595. Yeah. Give it a 96. Okay, next up we have, for the next one we have here, okay, yeah, so for this right here, we have observed a 15. However, our expected one was 13.97, and we whole square that difference divided with expected itself. Which is 0.0759. Okay, moving on, let's calculate the observed frequency. I mean the observed minus expected, so it's going to be 23 minus 19.38, and then we whole square that difference, so we get here our next value, which is 0.676. okay, so it's going to be 0.6762. let's keep it at 2. Okay, and then next up we have to do for these last two values here. So 11 minus 13.97, then we whole square the difference divided with 13.97 itself. So it's going to be 0.6314. Moving on, we have the last one, 8 minus 6.34, then we whole square the difference divided with 6.34 itself, and then we get here 0.4346. Right, so now we just need to sum up all these values and get a test statistic. Okay, so let's just add these up. 5, 6 plus 0. And finally, we have 0.3577. Let's keep it to 4 significant figures because all our values in every single test is in 4 significant figures. So yes, let's compare. To get our critical value over here, we've used 5 values to get our test statistic. So our critical value will be, well, our degree of freedom, sorry, would be 5 minus 1, which is 4. So that's the degree of freedom right there. So let's note it down red. So when we have here for a chi-square test, and degree of freedom will be the lower kind of exponent, like the subscript 4. Now we have our p-value. P-value is going to be 1 minus whatever percentage is here. So 1 minus 5 percentage, so it's going to be 1 minus 0.05, which is 0.95. So let's put here 0.95. Okay, so what does this mean is that we're going to look for a p-value of 0.95 with degrees of freedom 4 in the chi-square distribution tests. So yeah, 0.95, 4 degrees of freedom, so it's 9.488. Right, perfect. Now we just compare the test statistic and critical value, but before we do that, a step that you should always keep, you can keep this towards the middle parts for chi-square tests, but you can say H now and H1. Alright, okay, yeah, let's call this. Okay, so this is going to mean, man, that the distribution fits the data. Other one would state that distribution does not fit the data, and that's pretty much it. Yeah, that's the stating of our hypothesis. Okay, moving on, let's do the final comparison. That should do everything. So our critical value versus test statistic. Okay, so test statistic is 3.578. Compare that with the critical value, which is obviously greater than the test statistic. So since the critical value is greater than test statistic, we obviously accept H null. H null meaning the null hypothesis. Okay, and whenever we accept the H null, we state that there is there is insufficient evidence. Okay, something's going wrong. Okay, yeah. There's insufficient evidence, and okay, it says it's a claim. Okay, so whose claim is it? Okay, it just says that it is claimed. Fine. So you can say that there is insufficient evidence to support the claim. Okay, and that's chi-square tests. Fine. So CRV, or continuous random variables, we need to find the value of a. So this is really simple, quite straightforward actually. So you know that a is a constant. Okay, that's one thing that you need to know. Second thing is that when we have to find the value of a in when we have a PDF, you should know that when you integrate PDFs, you get a certain value, and when you plug in that value with 0 and 1, in this case our limits, we're going to get we're going to sum up all our functions to 1, meaning that the integral of the first function and second function sum up to 1. So doing this we get, let's integrate, so a plus 1 by x by 5 with respect to dx. Okay, and we have limits 1 0. So when we integrate this, we're going to be getting ax okay, ax plus x squared over 10 over 10. Okay, I'm just gonna zoom in a bit. Yeah, okay. And for limits 1 0, so when you plug in 0, it has no effect to this entire thing, so you're just gonna plug in 1, and we're gonna get a plus 1 by 10. So the first part. Next part I'm gonna denote in red. So next part 2, and let's integrate this function right here. 2a minus 1 by 5x, or x by 5, with respect to dx obviously, and when we integrate this function, we're going to get 2ax, and we minus that with x squared over 10. Oh, and I did forget that we need to put our limits. So 2 1 2 1, and when we plug in the values of 2, we get 4x, sorry, we're gonna get 4a minus 4 by 10. Subtract that with 1, so it's going to be 2a. Since we're going to have the minus of the entire bracket, this is going to actually be plus. It's going to be plus 1 over 10. It wouldn't be plus though. Yeah. Yeah, 1 over 10. It's going to add up 1 over 10, and when we solve this, you get 2a minus 3 by 10. Okay. Yeah. So now when we add up the two things, let's add up the first one and the second one. So when we add up this with this, we should get 1. So basically we're going to get 3a, and 1 by 10 plus negative 3 by 10, it's going to be negative 2 by 10 or negative 1 by 5. So negative 1 by 5 is equal to 1, which means a is equal to 1.2 over 3. 1.2 over 3. 6 by 5, which is 1.2. We divided by 3, it's going to be 2 by 5. Equals to 2 by 5. They usually like in fractions, but you can put it in decimals if you want. So 0.4. Okay, moving on, find ex squared. Okay, not gonna be too hard. Let's see. Find ex squared. Fine. So we need to multiply x squared with all our integrals. So over here we have a plus 1 by 5x. Okay, since a is 2, okay, let's not go there in depth. So let's just have an integral here, and we're gonna have limits 1 0 as obvious. We're gonna have 2 by 5. I'm multiplying the entire thing with x squared, so let's put x squared plus 1 by 5x. No, wait, it's gonna be 2 by 5, yeah. X squared plus 1 by 5x times x squared is going to be x cubed over 5. Yeah, it's going to be x cubed over 5 with respect to dx. Okay, now we can just integrate this. Okay, so when you integrate this, fine. So 3 times something. So 2 by 5. So 2 over 15. Okay, so I've got the fraction for the first one, fractional coefficient. Okay, so that's the first part, and the second one here, x cubed over 5 is going to be 5 over 4. It'll be 5 over 4. Yeah, it's going to be 5 over 4. It's going to be 5 over 4. Okay. Wait, no, it's not going to be 5 over 4. Let's see here. So 4 to power, okay, so it's going to be 1 over 20. Got a bit lost over there. Okay, now we have to plug in our values, our limits. 1 0. Okay, so once again 0 will have absolutely no effect to this entire thing, but 1 is going to have 2 by 15 plus 1 by 20. So let's just put that in. 15 plus 1 over 20, which is equal to 11 over 60. Okay, moving on, the second equation. Let's go green. Okay, so we gotta integrate. Okay, so to integrate this with 2 1 limits. Okay, so to integrate this with 2 and 1 limits, we have here a, that's going to be 4 by 5. 4 by 5 minus that with 1 by 5x. Okay, so we're multiplying the entire thing with x, obviously x squared. So we're going to have here x squared minus that with x cubed over 5. Okay, fine. And with respect to dx, we can get, okay, so for this one we're gonna get, let's see, so 4 over 5, oh wait, 0.83, so 4 over 15. Right, so this is going to be that section there, and for this one we already solved it. We got 1 over 20, but it's going to be negative this time, so 1 over 20 x to power 4. Okay, and this time the limits, both limits matter. So let's just plug this into our calculator and then get our values. So 4 by 15 times it with 2 to power 3 minus this with 2 to power 4 minus 20. Okay, and then we're going to subtract that with the exact same thing, except we're going to plug in 1 into our lower limit. So we're gonna get 415 once again, times that with 1. Actually, just need to keep it like this, so 1 will have no effect in terms of the coefficients. So we're gonna have 67 over 60. Yeah, okay. 67 over 60. So let's put that here. Okay, so let's add up our values. So it's going to be 11 over 60 plus 67 over 60, which is 78 over 60. And let's simplify that. We divide both sides by 6. So 78 by 6 should be 13. Yes, it should be 13. And if you divide the denominator by 6, you're going to get 10. It's going to be 13 by 10 or 1.3. 3. So they like it when it's in exact values. So let's put ex squared equals to 1.30. Fine, moving on. Wait, did I skip? Yeah, I did skip. Okay, find the CDF of x. Okay, not gonna be too hard. So we've already integrated the first part of the entire function. We got this part right here, except that we need to have x, so it's gonna have ax plus x squared. Okay, so for the first equation we had 4 by 5. No, it's gonna be 2 by 5. Ax plus x squared over 10. Right, so this is what we had earlier on, and then we can simplify that into, let's factorize 1 by 10 out of this entire thing, so that we get non-fractional coefficients. So for this, if you factorize 1 by 10, you're gonna get 4x here, 4x, and then we add that with x squared. That's our first one. Okay, moving on to find the second one. It's going to be a little bit more trickier, but it's still just as fine. We're going to plug in our upper limit of the first equation, so f of 1. So when we plug that in, we get 4 plus 1 squared, and that's just 5, and 5 divided or multiplied by 1 by 10, which is just 1 by 2. f of 1 is 0.5. So we're going to add 1 by 2 to our entire integral here. So 1 by 2 plus the integral of, so our upper limit becomes x, our lower limit becomes the one we had as before. The one we had before. And we're going to integrate the very first function, the second function here. 2a minus, or 2a will be 4 by 8, 4 by 5. Minus that with x squared by 5, no, x by 5. Was that it? Yeah, that was it. Okay, so when we integrated the, in terms of a, we got this right here with different limits. This is before we substitute the limits, so it's going to be fine. And do note, and do take care of this as well, that you can't really put x when you're going to, before we integrate. So we're going to take it as t, and we're going to differentiate with, integrate with respect to t. So you get 1 by 2 plus, remember this 1 by 2 is coming from this. We need to add this to this. So we're going to get here, and we've already integrated for this. Instead we had t last time, so 2ax, which is just 4 by 5t, minus t squared by 10. So 4 by 5 t minus t squared by 10. Okay, and this is for limits x and 0, x and 1. So we're gonna have 1 over 2 plus, going to be here 4 by 5x minus x squared over 10. We're going to straight up subtract everything, so minus 4 by 5, and minus minus becomes plus, so it's 1 by 10. Okay, so let's just simplify everything inside the bracket. We're going to get, and we can also factorize, so it's going to get 1 by 2 Okay, we don't have much space remaining, so let's just cut it a little short. So we're gonna get 1 over 2 plus, let's factorize, and you get 1 over 10. So when you factorize this, you get 1 over 10. That means 8x here. 8x minus x squared. When you factorize this, you get negative 8 here. When you factorize this, you get positive 1 here. We can't simplify this, so we're going to get negative 7. Negative 7. But now we can take this negative 7 outside the bracket. Okay, so what I'm going to do is I'm going to multiply 1 by 10 with negative 7. So you get negative 7 over 10. 7 over 10. And so now we just need to add 1 by 2 with negative 7 over 10. But given that we don't have much space, let's just write our final answer. So CDF always written in capital F of x. So f of x is equal to, now let's just put in our entire big bracket. So we're going to have 0 when the range of x is lower than the lower limit of the first function. It was 0. Okay, this is the range that you need to know. Next up, we need to have the CDF of the first function, which is this right here. 1 by 10. Okay, yep, and that's it. Moving on, we got for this range we have from 0 to 1. Let me just see the greater than equal to signs. Yeah, there is. Okay. Okay, moving on, we have for this right here, when you add 0.5 and this one, you get negative 0.2, obviously. So 7 over 10 is just negative 0.7. It's minus 0.1. Oh, negative 1.5. So we have 1 by 10, 8x minus x squared minus 1 by 5. This is between the range 1 to 2. Okay, and this is one otherwise. Well, no, not one otherwise. This is in PDF. So this is going to be greater than the upper limit of the second function, or the higher function, as I like to call it. Right, and this is our CDF. Moving on, we have a Wilcoxon rank sum test. Okay, so for this one, I'd suggest numbering in ascending order first. So let's start test A. Let's rank them in ascending order first. So we're gonna have the lowest value, which is 12. Okay, followed by an 18, then 25. Okay, it's going a bit unsynchronized, then 29, 32, 33, 40, and 46. Yeah, this is right. Okay, fine. Let's go to test B now. Fine. So for test B, we need to do the same thing. Yeah, there's no exceptions to it. So we're going to start off with quite a high value. So it's 28. Then we have 31. Moving on, we have 35. Then we have 36 here. 37. Then 41. 48 and 49. So okay, so let's rank them now. So in ascending order, we have here the lowest value, which is 1, which is 12. We're going to rank them with the lowest value from 1. So we have 2 next. This becomes 3, This right here is our first value, which is going to be 94. 5, 6, 7, 8, 9, 10, 11. Then we go on to 12 here, 13, 14, 15 and 16 go here. Okay, so that means that we have our values. And one crucial step I forgot is the hypothesis. Okay, so in this state they're seeing whether there is a difference in the population median. This is a hint. This is a hint that's a two-tailed test. So median 1 is equal to median 2. So this is a constant for any null hypothesis. It always stays the same for Wilcoxon or any test, actually, even t-tests, except we have means instead of median. Here it will be m1 is not equal to m2. So m1 can either be greater than or lesser than. So we're going to look at both sides of the tail, meaning that it's a two-tailed test. Okay, so moving on, let's find our test statistic. So our test statistic right here, I'm gonna call this Rm. Rm is equal to sum of all this. Okay, so 1 plus 2 plus 3 plus 5 plus 7 plus 8, 12, 14 is equal to 52. Okay, so the next one, since we're numbering them from 1 to 16, right? That's totally, yeah, so we're going to number them from 1 to 16, and given that there are totally 16 samples we're numbering, and so we can just use summation formula to find the total sum of everything, and then just subtract that with 52. You can get this, it's 84. You would have learned summation of series in pure 3, so this is quite an applicable formula. We can still test it though if you want. So it's going to be 4 plus 6 plus 9 plus 10 plus 11. Yeah, it's 84. Okay, so now to find the test statistic, t is equal to the minimum of Rm comma Rn. So which one's the minimum one here? It's obviously Rm, which is equal to 52. That means, okay, so t is equal to 52, our test statistic we found. But for every test we should have a critical value. Let's find it. So for a sample size, okay, so it's going to be 8 and 8. Okay, so m and n, let's see, yeah, right here. So m n is here, 8, 8, 8. Okay, so we're going to look at these three values here where it corresponds from m equals 8, n equals 8. M and n being two sample sizes, as we have here test A and test B are both 8 and 8. Okay, so let's move on with this. Which value do we take? So it says that's a 5% significance level test. So we have a hint it's either this one or this one, because those are the only ones corresponding with 5%. But you know that it's two-tailed test because they're testing for any kind of difference in it, not like whether m1 is greater than or lesser than m2. So it's going to be this column right here. That means 49 is our critical value. So we're going to say critical value from tabular column is 49. Okay, and yes, now the most classic step of every single test is comparing the test statistic with critical value. So yeah, whoops. So since the test statistic is greater than critical value for a non-parametric test, we accept H null. Okay, and since we accept H null, we're gonna end it with the most used statement. So it's gonna be insufficient, or there is insufficient evidence to state that there is difference the means, no, difference in population medians. Okay, moving on. Interviewer considers using given information to carry out a paired sample t-test to determine whether there's a difference in the population means. Okay, so a paired sample t-test, sure. Okay, why this would not work? Really simple. It says that they took from 8 applicants from A and B, 8 applicants of A, and then a random sample of 8 applicants who took B. If these 8 applicants were the same, we are knowing that it's going to be paired because one person took 2 tests. However, we are taking 16 different people and giving 8 of them one test and 8 of them another test. So we know that we can't group any 2 people from these 8 and 8 groups together. That means that paired t sample test is out. Wilcoxon matched pairs test is also out. So rank sum remains to be our best estimate for the test. So yes, to emphasize that in a word, it would say that samples used are not paired. This is the first part. Okay, this is the most important part that you need to know. Okay, and secondly, now we're gonna have the assumption of the distribution. So we're gonna say that underlying distribution is not assumed to be normally distributed, or since we mentioned underlying distribution, we just say normal. Yeah, we can say it's not assumed to be normal or known to be normal. Yeah, any of them is fine. So moving on, we have here PGF. Okay, really simple. Find the value of k. So PXR, okay, very simple. So for r equals 1, 2 and 3. Okay, fine. So when we take in r equals 1, when r equals 1 we have k. When r equals 2 we have 4k. When r equals 3 we have 9k. When r equals 4 we have 16k. And do note this will all add up to 1. It's all equal to 1. We can factorize k out of this entire thing. We're going to get 1 plus 4 plus 9 plus 16, which is equal to 30. 30k. So k equals 1 over 30. Equals 1 over 30. Okay, that's perfect. Find the PGF. Okay, so this is quite straightforward actually. So we're gonna just we're just gonna pair it up with the values of r here. So we're gonna have 1 over 30. So when r equals 1, we're gonna just have k at r, k being 1 over 30, r being 1, and since r is 1, our t is also to the power of 1. It's gonna be t, and similarly we just repeat for the others. So it's gonna be 4 over 30 9 over 30. I don't think we need to factorize these because, well, I don't see any need to do it. So, and lastly we have 16 over 30 e to the power 4. Okay, so this is our PGF for this. In a way that we would easily be able to do it, I would suggest factorizing this. Okay, but make sure this isn't our answer. We're gonna have to make sure that this is not our answer. So just keep this in brackets so that we can use for later. It's gonna be 1 over 30t for t plus 9t squared plus 16t cubed. Okay, so this right here is our factorized form. This is going to be useful because they're gonna ask us to sum it up. I know they will. Yeah, they will. By the way, this isn't 36, so let me not emphasize any kind of troublesome things on that. Okay, yeah. Moving on, assuming that x and y are independent, find the PGF of z. Okay, now what we can do with this is that we can factorize gy of t as 1 by 4. Put this in brackets. We have 1 plus 2t plus t squared. Okay, this looks like it's the PGF of getting a heads or tails when you flip a fair coin. But yeah, 1 by 4, we have this is a perfect function. Now we need to just multiply the two functions. So really simple, we just do 1 by 4 times 1 by 30, which is 1 by 20, 120. And we multiply this with, okay, now this is where it gets tricky, because you're going to have here 1 plus 2t plus t squared. We're going to have to multiply a lot of terms algebraically, but it's still very easy. Plus 4t okay, so this right here is all that we need. Perfect. Okay, so this is the gz of the PGF of z, but we need to obviously simplify this further. So it's going to have, okay, let's just exclude this for a minute. So I'm just going to simplify this right here so I don't have to repeat our steps. It's going to be 1 plus 40, so I'm just going to rewrite the equation basically, plus 16t cubed. Okay, so now that we've done that, that is our function. Yeah, it is. Okay, now that we've done that, we just do for 2 now. So it's going to be 2t plus 8t squared plus 18t cubed I think it should just specify this is a cube. Yeah, that confused me as well. So this is 32 t to the power 4, and then we add that on with now our t squared times everything. So t squared plus 4t cube plus 9t to the power 4 plus 16t to the power 5. Okay, so let's just see if everything is right. So far the first one I know it's right. Second one, yes, second one looks to be right. And so the third one is also right. Fine. So this, we can simplify this. So we have 1 here plus all the terms of t is going to be 4t plus 2t. So it's going to be just be 6t. Yeah, so 6t plus t squared now. T squared, t squared, t squared. So it's going to be 12. Let's see. 1. So not 12, sorry. It's going to be 18. 18t squared. Moving on, we're going to have here. Okay, so the t cubed is going to be 16t cubed plus 18, which is 34. 34 plus 4, which is 38. So it's 38 t to the power 3. Now we have t to the power 4. Really simple again, just adding up 32 to the power 4, and it's going to be 41 to the power of 41 t to the power 4. We add that on with final one, 16 t to the power 5. Okay, so this is the simplified version of the two polynomials given here, and we need to multiply the entire thing with 1 by 120 t. So I'm going to just factorize 1 by 120 out, because nowadays these past papers, they actually permit factorization of polynomials. So let's write our final answer. We're just multiplying t inside all of this, because we factorize 1 by 1 by 120 t. So we're going to just multiply the t inside, and we're going to keep 1 by 120 out. So we get t plus 60 squared plus 18t cube plus 38 t to the power 4 plus 41 t to the power 5 plus 16 t to the power 6. That right there is your PGF of z. Now they're going to ask us to find the variance of z. Very simple again. So let's just differentiate z with respect to t. Okay, we need to differentiate it once. And they're already given our expected value, so it's not going to be much of a hassle really. So 1 by 120 of 1 plus 12t plus 3 times 18 is 54, if not wrong. 54 squared plus it with 38 times 4, so what was that? 152. Okay, so 152 t to the power 3. Then we have 41 times 5, which is going to be 205, but let's just make sure it is right. Yeah, 205. So it's going to be 205 to the power 4 t to the power 4. Let's just see if everything's right. T to the power 4, yeah, t to the power 4. Finally, we're going to have here with 16 times 6, which is 96. Yeah, 96. 6 with 5. Yeah, 96 with t to the power 5. So this is our single differentiate, and we can plug in t equals 1 to get 13 over 3, but that's already given, so why waste time? Instead, let's double differentiate. So when you're double differentiating this, you get 1 over 120, and now our constant goes away. We're going to get 12 plus 108 t plus now 152 times 3. I think it's going to be 456. Yeah. Then t to the power 2 plus 205 times 4, 820, I guess. Yeah, it's 820. So 820 t to the power 3, and finally 96 times 5. So 96 times 5 is 480. So 480 t to the power 4. Now we just plug in t equals 1. So gz double dash 1 is equal to, so when you plug in, we're just getting the coefficients. So 1 over 120 times it with 1 plus, so now 1, it's going to be 12 plus 1 of 8, 456, 820, 480, and this right here is going to give an answer going to be 469 over 30. Fine, so that's our value right there. 108. Yeah. So value is going to be this idea, 15.63. Yeah, should be fine. Next we can just do the variance calculation. So variance is equal to, so x is equal to gz double dash 1 minus that width, no wait, plus that width, gz dash 1 minus that width, the square of gz dash 1 squared. Okay, so using the same formula we can just do 469 over 30 plus 13 over 3 minus 13 over 3. Why is it going like that? Okay, minus 13 over 3 the whole square. Okay, and so answer plus 13 over 3 minus it's going to be 107 over 90. So have here 107 over 90 is equal to 1.18119. Yeah, so let's just write this in a box. Variance of x is equal to 107 over 90 is equal to 1.19. Yeah. Okay, now last question. It's a 10 marker question and it's going to be quite a big one. Fine. Sure. I've done this kind of a question before, so it's going to be quite simple. So obviously we're going to test the test. For whenever we're doing a testing, we're going to have to get our hypotheses. So in this case it states that the mean mass of A is greater than the mean mass of B. So mean A equals mean B. That's a null hypothesis and that forever will be. Our alternative hypothesis, however, will combat that and it will be what's written over here. So mean A is going to be greater than mean B. Okay, moving on, we have here, okay, so this is where all the 10 marker process comes in. So we have sum of x. Okay, let's not write that here, let's write on top of the page. So the sum of x is equal to 2.1 plus 1.8 plus 0.9, 3, 2.4, 2.6, 1.8, okay, 1.8, 2.2 plus 1.9 plus 2.5, and this is equal to 21.2. So let's put that here. Next you're gonna have sum of x squared. This is also following the same procedure except we do square for everything. So it's going to be 2.1 squared plus 1.8 squared plus 0.9 squared plus 3 squared, 0.4 squared. Yeah, this statistics based question is quite tedious to do but really simple. It's like a free 20% of the entire paper. So yeah, this is definitely worth it. 1 squared plus 2.5 squared, so that is equal to 47.92. The very last thing that we need to calculate is the sample mean. That is equal to 21.2 divided by 10, so that is just 2.12. As for y, we need to calculate the sample mean as well. Sample mean for y has 12 fish, so 24.48 divided by 12, it should be, now I'm gonna guess this one, it's gonna be 2.04. Yep, so that's it. 2.04. Okay, moving on, we need to calculate s2x, s2y. Okay, so this s2 of x is equal to 1 by number of samples of x. How many number of samples we have? 10. Minus 1 obviously, so it's 1 by 9 of 47.92 minus that with 21.2. Yeah, 21.2. 21.2 square that, whole divided with 10, and we have here 47.92 minus 21 by 10. Okay, so this divided with 9, so 124 by 375. So this is the value that we're going to use in calculator, or in calculations actually. So we're going to put this on screen. This is the value that we're going to use on screen. However, this is the value we're going to put on our paper, just so that they know we have the decimal value indeed. Okay, so for s2y we follow the same logic, except we just use the y values. So it's going to be 1 by 11 this time, because s has s2 of y, y has 12 samples. This is 53.75 as the sum of y squared, and minus that with 24.48 squared. Divide that with 12. Okay, so going on with this, 3.75 minus, and divide that with 11. Okay, so quite a big fraction, but quite a small value. So I have this here. And this is the same as 0.34644. Let's give it a 44. Yeah. Now I'm going to do, they said that we can state any assumptions that you make the test to be valid. So I like the pooled estimate formula a lot, so I'm going to use that one. You can choose any method you want. You could just use the normal S2 method, although that's a really boring formula, and it has not a really good assumption that we need to use. So S2 of P is equal to S2x, that is 0.33. and you know what, I'm just going to mention S2x. So it's S2x times that with number of samples minus 1, so it's times that with 9, and then we add that with S2y times with number of samples minus 1, so it's 11, whole divide that with number of samples of x, which is 10, plus number of samples of y, which is 12, minus that with 2. Okay, so when you do this, we got x value as 124 over 375. Okay, this is our S2 of x, and this is multiplied it with 9, and then we need to add this with S2 of y, which is 9. I think I saved it as answer, so answer times 11, and then this is entirely divided with 10 plus 12 minus 2, so it's just divided by 20, and this is equal to 0.33934. So 0.33934. Okay, now to move on with test. Statistic is going to be mean x minus mean y, whole divided by s times the root of 1 divided by number of terms of x plus 1 divided by number of terms of y, and then we close the square root. So mean x minus mean y is going to be this. We'll divide that with root of s2p times that with the root of 1 by nx, which is 1 by 10. Any value that's a bit too big to fit in, I just mentioned their variables. They should be fine with that. And yeah, so 2.12 minus that, it's going to be 0.08, but for the sake of it, let me just put that here. Root of 1 by 10 plus 1 over 1 by this is equal to 0.321. Okay, we're going to compare this with the critical value. So how do we find critical value? So let's first reference this. So to reference critical value, we're going to have a degree of freedom. So for that, it's going to be 12. It's going to be it's going to basically be the denominator of the pooled estimate. So 10 plus 12 minus 2, which is just 20. So let's go to the t values. T equals to 20. We're going to have here huge lots of sets of values. Moving on, we have to look at the significance level. So it's a 10% significance level single tail test. So it's going to be this right here, 1.325. So we're going to compare. So yeah, so our degrees of freedom was 20, comma our p value, which is 0.90. This is equal to 1.325. Okay, now we compare. 1.325 is obviously greater, which means that the critical value is greater than the test statistic, and that too by quite a margin. So we're going to accept H null. We accept H null, and since we accept H null, before we do this, I think we should state our assumption. Now we'll state our conclusion first. Okay, yeah. Since we did accept H null, we're going to say that there is insufficient oh never mind, to state that mean of A is greater than mean of B, and that's right there is your answer. As for the assumption, let's put it like this: assumption. Okay, yeah, now we can say that distributions always need to be normal for this kind of test. So distributions are normal, and since we are using pooled estimate formula, we're going to say distributions are normal with both populations having equal variances, and this right there should conclude that question. There are alternative methods for doing with S2, but yeah, that's pretty much it for that question as well. And that sums up basically the entire paper. I hope you learned something new. Please don't forget to like, share and subscribe, and I guess I'll see you until next time. This has been Further Statistics October number 2021 series, the paper 4.2, and this has been A Level Up. Thank you for watching.